Hello and good morning. I would like to thank everyone for joining in today for our guests. And as a refresher for most of you, I am Isaac Hill, a second-year master's student and steep trainee with Dr. Reiner Lohman here at URI-GSO. But today's focus is on our seminar series guest speaker, Mark Strynar, who is with the U.S. EPA out of Research Triangle Park, North Carolina. Before we kick off this seminar, I would politely ask that the audience mute their mics for the duration of the presentation. You should also know that this virtual session will be recorded and Mark's seminar will be available through Steep. Following Mark's presentation, I will moderate a brief Q&A session. So I would ask that if you do have any questions, please prompt those at the very end down in the Zoom chat section below. And I will try my best to read through and get through as many of those with Mark as possible. So to kick things off, a little bit of background on Dr. Mark Strynar. Mark is a physical scientist in the Office of Research and Development of the US EPA and RTP and has been there since 2002. His research has included the use of high-resolution mass spectrometry to investigate the fate and transport of PFAS and other xenobiotic compounds and a variety of environmental and biological matrices. And I believe it is safe to say that Mark has certainly been on the forefront of novel PFAS discovery, as well as analytical method development. And we are very excited to host him here today. So without further ado, Mark, welcome, and I will turn things over to you.
Okay, thank you, Isaac. And can you just let me know, let's see, one moment, if I am full screen?
You are now full screen.
Excellent. Well, thanks for the opportunity to do this virtually. I honestly really would rather be there, even though it's apparently snowing. Last spring, I was having dreams of going to Aunt Carrie's to have clam cakes and chowder. For those of you who don't know, I'm also a URI graduate and I have family and friends that still live there. So it was going to be a dual purpose visit, but I'm glad to tell you about the work that I do. And I think it's one of these jobs that I often dreamt about when I was an undergraduate and a graduate student, where I often look back and think, wow, I get paid to do this job. And on a daily basis, it's exciting, fun work. And I get to collaborate with neat people from all over the world, including people at URI. So I'm going to launch into the mechanics of how I do the work that I do. When I say I, it's really not me only. I'm surrounded by a group of people and have been for many years, whose names would be too numerous to mention here. But we have a very good group of people that do this work alongside me and with me. And I do a lot of screening, and I often want to say, why do we screen for chemicals? And if you think of chemicals as sheep, I think we're looking to find the wolf in sheep's clothing. We're not really interested in looking for chemicals just for the sense of finding them if they're not problematic. We really want to find the ones that potentially could cause grief to people and undue harm, either ecologically or with human beings. But I think more importantly, we probably want to identify those wolves that are just among the sheep. So the things that stand out, they're not masquerading as a chemical that you and I have in our bodies or is naturally occurring. They're the things that really just sort of stick out. They're xenobiotic. They're made by man. They're persistent, bioaccumulative, and toxic. And perfluorinated chemicals and polyfluorinated certainly fit that bill. And the dilemma that we all have if you work in a lab is we're trying to isolate the chemical of interest from the milieu or the matrix. And here the mouse on the elephant's nose. And trying to get rid of that matrix interferent is most of the job that I have to do, because the perfluorinated chemicals or other things I look at are present, but I have to pull them away. And for those of you who work on either humic substances or proteins, I'm sorry if I call your very important work, matrix interference. But as an analytical chemist, trying to find the small, low molecular weight compounds like PFAS and pulling them out of these giant structures, polymeric in nature and multifunctional, is a lot of effort. And that's often where most of my time is spent. Now, how do I look at data? I often think of building a case for what requires additional investigations. And it's not simply something that I can just sort of read in the paper and convey into my own work. And it's sort of like a police lineup, trying to figure out who it is that did whatever the dirty deed was that was done. You can sort of look at this picture and sort of decide for yourself. But As it comes to xenobiotic compounds, that's often things that I think of like big peaks. I don't want to really spend all my time on really tiny, small, insignificant peaks, that are found frequently in samples, detection frequency. If they have a halogen on them, I'm going to talk a lot about fluorine today and chlorine, but bromine and even iodine could be present. I'm going to talk about mass defect. This is something everybody might not be familiar with, but perfluorinated and polyfluorinated compounds have this unique characteristic that sets them apart. And then the last thing is homologous series. These often do not exist as only one chemical. There's a series of them. And when you put together all of these pieces of information, it's sort of building a case for the things that require more investigations. So, and the reason I do the work I do, and I think it fits into the work that a lot of people on this call probably do, is we're trying to make decisions. And I equate this to like your home. Your home is built on a foundation in New England around here. It's built on some sort of a crawl space, but it's critical. It's the first step. If that's done wrong, everything else that's built upon it sort of fails. And compound identification is the basement upon which all the decisions we make about these chemicals sort of are built upon. You can say nothing about occurrence if you don't even know a compound is there. Certainly, you can't say anything about risk because you don't yet know about it. And remediation also hinges upon once you know the presence of the chemical and can quantitate it, you can make decisions as to whether or not a site has been cleaned up. Again, those are all built upon this very foundation. And I work down in this foundation level, which I really enjoy because I think that's where a lot of the really exciting work to be done is. So if you don't do high resolution mass spectrometry, I would recommend that you look at this paper down here. It's written by Michael Balo, who works for, at the time it was Waters Corporation. He goes into some good detail about, well, what is it that a high res mass spec can do? And he talks about resolution, and resolution is really the ability to differentiate an ion from another ion. And for those of you old enough to remember a tube TV, this is sort of low resolution mass spectrometry that we all do, whether it's a single quad or a triple quad. Yes, you can do the job. Yes, you can do lots of very good work. I still do this. But when you do high resolution mass spectrometry, it's a higher ability to sleuth out what it is that's the chemical that's present, the formula. You can get fragments to a high degree of certainty. It's sort of like the difference between a high res TV and a low res TV. Both do a particular job. One just does it better than the other. And the second thing about high resolution mass spectrometry is mass accuracy. So this is the ability to measure a molecular weight. And in this example, I am a woodworker, so I'm always measuring out in my shop. Here's a piece of wood that, I can measure with this ruler from a yardstick my wife had, in her craft room. I can still get a pretty good measurement, much like on a triple quad, molecular weight plus or minus 0.1 to a half a Dalton. Whereas on a high resolution piece of equipment, like an Orbitrap or a QTOF or something like that, you can measure that molecular weight to the fourth decimal place with a high degree of certainty, much like I can do with this better ruler. And again, Michael Balo talks about this. The unit we use is ppm. And the better you can get at measuring this molecular weight of an intact molecule or a fragment of a molecule, the better you can be at predicting that formula. And if you cut down the number of formulas, then you can better sleuth out what it is that you need to get for a standard if it truly is that compound. So mass accuracy and resolution go hand in glove. And that's the other thing I sort of want to point out. And a lot of the work that I do, and this is probably not news to anyone here, we're looking at a very small portion of the chemicals that out there in the world when we do our analysis, much like this iceberg, what's underwater versus what is above water. And I often have to ask myself this question: how comfortable am I on this entire continuum of not knowing what any of the chemicals are in a sample to knowing what all of them are? I don't think I'll ever approach this 100% known, and I don't think I'm ever in the 100% unknown, but where am I on this continuum? And in particular, on a lot of the environmental samples we work on, they're extremely complex and there's many thousands of chemicals. What is it we need to know and what is it we don't need to know? And that's a personal decision, often based on the work that's being done. So if you're not familiar with targeted versus non-targeted analysis, just a brief primer. Targeted analysis is much like shooting at a target with an arrow. I'm looking for a particular chemical with a validated method, fipronil in this example. And on the bottom, I'm looking at through non-targeted analysis using a high resolution mass spectrometer. Low resolution triple quads are very, very robust and good for the TARP portion. But to do the bottom portion, you require high resolution mass spectrometry. And it's a different question that's being asked, such as what chemicals are in my water? And there are two ways you can do this. Suspect screening is essentially, it's already known that chemical exists. You have a large database of chemicals. You screen your sample and you run it against a database. But what I also do is I do this true non-targeted analysis, which is if it's not already in a database and there's not an existing method, we need to do novel compound identification. And this is really where high resolution mass spectrometry shines. And this is really where we've done a lot of our recent work. And I find most of the excitement here to then add back to the suspect screening pile so others can look and then get standards so people can then start doing targeted LC-MS-MS methods. It's sort of a feedback loop. So the first key tool that we use, and if this is not something you've heard before, please just pay attention to this slide in particular. Mass defect is a term we use to pull out chemicals that deviate slightly from the norm. And for example, I'll just sort of highlight a few. These are the most common elements we look for in a lot of environmental samples. Carbon being mass neutral, it's 12 with 4 zeros after the decimal point. And every time you add an element to that carbon, we're talking organic chemistry, the ones here, a hydrogen or a nitrogen, give a positive mass defect. And if you add oxygen through to bromine, iodine should be included here as well. They give a negative mass defect. And all that essentially means is the whole number. If it's less than a whole number, it's a negative mass defect. If it's more than a whole number, it's got a positive mass defect. And most of the endogenous compounds you find in your body have a positive mass defect. Anytime you add a halogen, it imparts a negative mass defect. Most of the chemicals that I'm going to talk about today, because they're highly fluorinated, get a negative mass defect or they've got a chlorine on them. And what I want to point out is that for an example, AFFF, those of you familiar with aqueous film forming foam, it takes 4.8 hydrogens. It takes 4.8 fluorines to overcome one hydrogen. So if you've got a perfluorinated tail on one end, and then you've got a hydrocarbon on the other end, they sort of kind of are diametrically opposed and they cancel each other out. So this is not as good a technique to find AFFF components. There's other ways to do that. But with polyfluorinated compounds in homologous series, this is a key feature that I use to pull things out that are different from the norm. Octanoic acid here has a positive mass defect only made up of carbon, hydrogen, and oxygen. Here shown that it's slightly more than mass 144. But if you fluorinate that fully, even though the molecular weight increases dramatically, it's now slightly less than a whole number. And this 0.9 on the end is the thing we glean in on and look for. And so that's a tool that is critical for the work I do. The other thing I like to sort of think about when I look at data is, well, how many features am I finding? And here a feature means a mass to charge and a retention time in an area. So on this graph, retention time on the x-axis, mass to charge on the y-axis, and the size of the dot or the sphere here is proportional to the area. And I pointed out a few here shown in red. There's 5 red ones, one sort of hidden, and a little green one that I want to spend some more time on. But what I want to say before that is it's not always important to identify all the numbers of features. Often it's important to identify many of the larger, more pronounced features that are found in lots of samples. And this is something not everybody is in agreement on, even within my own group. So I'll make a pitch as to why I think that's important. And I'll point out before I say that, within this whole milieu of sample features that I'm showing, in the first 100 peaks, this is sort of based on area count, 17 of them have a negative mass defect. And I know what 7 of them are. And in addition to that, there's 3 internal standards I added. So polyfluorinated compounds and xenobiotic species exist. So what I did here was I took that exact same data and I just rank plotted it based on integration. So I had to do it, log normal. Actually, this is log log to get it all to fit. But what I want to point out is these are the same 5 features I showed in the previous plot, this one in red and green. So that first peak is oleic acid. So this comes from sort of cooking in your home. This is from standard reference material 2585. It's the NIST SRM. So that one peak is more than 16% of the total integrated area of all features here. Am I worried about oleic acid? Probably not in my house dust, maybe more in my body. If I have too much of it, I probably get high cholesterol, some other health effect, but it's only one peak of more than 4,000. And by the time I get to this 15th peak, I'm approaching 50% of the total area of all features found by the time I get to this point. And this molecule is something we discovered some time back. My colleague Seth Newton published on this. I'm going to show it in the later slide, but this molecule is interesting. It's a perfluorinated tail with a tetrachlorothalate end. It's the first negative mass defect feature found in house dust, SRM 2585, and the patent literature says it was used for 2 purposes: for hairspray in the 1970s and for insecticidal purposes in the 1980s. So finding it in house dust is absolute something that makes sense. I know nothing about its toxicology, but I do know if you cleave this, you're going to have PFAS. So triclocarban was also found in this sample set. It's the 21st biggest peak on the list. And by the time you get there, it's a little more than 50% of the cumulative area. 2 of our good friends, PFAS and PFOA, by the time we get here, we're roughly 65 to 70 or 67% of the total area. And by the time we get to the 100th peak, so the 100th peak is nothing important, I just sort of plotted them this way, I can explain 75% of the total area in that sample by just explaining those first 100 peaks. Now, this is only 2.2% of the number of peaks. So the question I always ask is, does the rest of this make sense for us to spend a lot of time on? You can make a pitch one way or the other. I like to work up here in the area where the peak is big and I'm explaining things that are, xenobiotic and found often in large. That's not something everyone agrees with that does this kind of work. The other thing I would say is the mass defect space. So what I did here was I went out and I found this human metabolome database. So these are endogenous compounds found in your body and mine. And I simply plotted in this graph what it is within the mass defect space where these compounds live by frequency. And what I want to show you is, these are all the things found in the human metabolome. This is the PFAS master list that I downloaded from EPA's DSS Talks webpage. And I hope you can see, they occupy a very different molecular weight, mass defect space. The perfluorinated chemicals tend to be around this middle region where the compounds found in the human metabolome can split and is sort of devoid in this region. Second, I will say, those that are found on the EPA drinking water list, and this is about 31 compounds that you, me, and everyone in this country and possibly the world look for, exists in a smaller set within that PFAS database. So we're really looking for a group of compounds that sort of stand out alone and are in a region of mass defect space that are not normally found in our bodies and really in the environment. That's another way we can sort of tease these out. AFFF, again, is a little bit different. You can maybe widen that a little bit to find additional compounds associated with that. Another tool that we use mechanistically is Kendrick mass defect plots. And so I can't go into large detail about how you do this, but hydrocarbon people and carbohydrate people have been doing this for years. Again, it's a retention time plot based on mass to charge. The size of the ball is proportional to the area. If you take your data as just a list of molecular weights, here it is, mass to charge, retention time, volume, you can transform your data by simply taking this Kendrick mass, which is your observed mass, and you multiply by the ratio of the molecular weight here of a CF2 relative to the molecular weight or the exact mass of a CF2. And you can transform that data, take the nominal mass, subtract it to get this Kendrick mass defect. Long story short, what it does is it makes chemicals stand out that only differ by a CF2. So you might not know what they are, but you see a series of features that differ by only a CF2. You could put a CF2O here. You could put a CH2CF2. It doesn't really matter. You can transform it any way you want. And then you physically look at your data. I did this in Excel. You can also do this with some R scripts. I don't know the name of it offhand, but there's an R script that will let you take Orbitrap data and look for these homologous series. You need at least 3 in order to find. So taking the feature I already showed you before and getting rid of the bubbles, I transform this Kendrick mass on the x-axis and the Kendrick mass defect on the y-axis. And if I just zoom in on this region, because it's a very busy figure, I understand, I wanted to call out several things that I can show you just in that region. These compounds are the perfluorocarboxylic acid, starting with trifluoroacetic acid and going up as high as C12. You'll see they all fall on this line. They only differ by a CF2 unit. Just above that are the perfluorosulfonic acids, the smallest one being PFBS, the largest one being PFDS. Again, they fall on this line. And on the very top is that very compound I talked about earlier, this tetrachlorothalate attached to a perfluoro backbone. One of them is in the series. Here's the paper that we published on that. Seth Newton was the lead author. There's also a homologous series. There's likely other things in here that I didn't have time to go into, but it allows you to, rather than just finding one feature, finding 5, 6, 8, 10 associated features and really getting more bang for your buck. And the great thing about polyfluorinated compounds is they usually exist as a group. So putting this into practice, we've done a whole bunch of work in my lab on water, whether it's coming out of the factory that's emitting it, whether it's in the river receiving it, the soil that surrounds facilities. We do work on runoff and groundwater, and spent a ton of time. And in this conceptual model by Davis et al., this was actually at the DuPont facility in Parkersburg, West Virginia. They showed that likewise, air emissions can also contribute to the polyfluorinated compounds coming off. So we can go in and sleuth using these tools as to what is in the river before the effluent comes out, what is in the air emissions, in the air receiving that air emissions, and what is actually in the emissions. And it's just a comparison. It's a simple upstream, downstream, before and after, close to the facility, away from the facility, with groundwater, what's migrating deep versus shallow. And in particular, I think with air emissions, if you do some sort of a treatment to that air, some sort of a control treatment, is the treatment effective? You don't even really need to know what the chemical is, just does the treatment technology get rid of the chemical? That's a really good use for this. And so we've applied that to these very same sets of samples and to these very same tools that I'm talking about. In this example, the Cape Fear River, the plot is retention time versus mass defect I talked about earlier, and the upstream samples are in blue, and the effluent samples coming out of the Chemours or DuPont facility at the time are in red, and I circle those that are both in the effluent only and found to have a negative mass defect. They require more sleuthing. They're likely fluorinated. I don't know that they are. So I'll spend my time on these as opposed to every feature on this, because they're also unique to that downstream sample, meaning they've been put into the environment. And in doing so, what we found early on in this example, this is Gen X or HFPO dimer acid. As it turns out, that molecule doesn't really exist as an M-H peak. For those of you who have worked on that molecule, it's extremely fragile. And in most mass spec sources, there's a carboxylic acid right here that cleaves. And what I found when I bought the standard is it's almost non-existent. It's a peak down here that's not seeable, but we see some very unique fragments. But what we found in the source is that these compounds, these polyfluoroether carboxylic acids, really like to come together with a proton in the source to give these in-source dimers. Here, the example is with a proton, and here with a sodium. And those two compounds show up in the source, in the spectra, and they differ by this known molecular weight. And this molecular weight is the difference between a sodium minus the molecular weight of a hydrogen. And we started to use this as a tool to find polyfluorinated carboxylic acids that we're unaware of. Oh, look, we see a peak. It has a negative mass defect. And there's a second one, and they differ by this exact molecular weight. And I can go in with a caliper and measure that molecular weight. I should just tell you, you can see this with potassium, ammonium, And also you can get trimers and tetramers depending on how much is around. The more that's in the sample, the more of these things form. There's competition in the source for that ionization. So some other key tools we use are just these diagnostic fragment ions. And in this particular example, if you have a CF3 oxygen bust off, it weighs this molecular weight, and you can have additional in-source fragments. This 184.98 is very common. If you do perfluorinated compound work, the very tail is a 68.99. That's a CF3. And when you do MS-MS work, you can simply plot what are the diagnostic fragment ions. They might not be unique to just your chemical, but there's a series of them, and go and look more closely at that retention time for what is giving you that diagnostic ion. An additional one that we recently published on, this is going back to a poster. We've now published this in Science. There's this chlorinated tail that has an oxygen linker. And this was really unique because we had never seen that before. This is with our work we did around a Solvay plant in New Jersey. And I know Anna Roebuck is doing some work at that facility, and we are still seeing these compounds, and we'll likely be publishing some of this more with Reiner's help in the near future. So prior to the PFOA stewardship agreement, you should go look this up yourself. Most of us were looking at PFOA and PFOS, right? It really wasn't that complicated. And with the advent of the stewardship agreement, a lot of the manufacturers, either they were already making these compounds and not using them for polymer processing aids or for metal plating, but they started using them. And so we have a host of these polyethers. So you just see these oxygen linkers in the middle. And this is, 3M, this is Chemours, DuPont, Asahi, Solvay, et cetera, others. I call it like cutting off the head of the Hydra. You cut off one and you get two back. Well, we went from everybody working on PFOA to everybody beginning to work on, well, what else is out there? The additional thing they did is they made these compounds polyfluorinated. Formerly, it was just perfluorinated. Now we've got these carbon linkers in the middle that are hydrogenated in this example, or in this example, the telomere sulfonate. And last, I'll talk about this one in our own particular work. There's a chlorine put on the end of that molecule, which I always joke is a great idea, right? Polyfluorinated is not bad enough. Now let's chlorinate it, whether to use for polymer processing aids or for metal plating. And those really stand out when we do mass spectrometry work. So an application on the Cape Fear River, using the tools I've explained, it turns into a paper, which is, 3 to 5 pages, but this took, years of work. And when we published this paper, we could only find an authentic standard for Gen X at the time. Excuse me, let me get a sip of water. So this is a wall that we all hit when we do NTA work. You find something new and you're actually not sure if it's that, you have to get an authentic standard. At the time, I could only find HFPO dimer acid to confirm this compound. Every other compound on this list at the time was simply theoretical, and it was based on what we thought it was as a tentative structure proposed. As it turns out, we were right on all of these. And so I think with good chemists around you and a good high-res mass spec, we didn't even have a QTOF at the time. We only had a TOF. We were able to get to the point where we could figure out what all these are. And as it turns out, many of these molecules not only were in the water coming out of the Chemours/DuPont facility for, it sounds like, a number of years. We found them in the drinking water down in Wilmington, North Carolina, and it was in the serum of the people who were drinking that drinking water. This is no longer just accepted. It's actually, it's already been in press for quite some time. Nadine Kotlars, who works with Jane Hoppen at NC State, did this work where we could find a series of these molecules. This is Naphthalene byproduct 2, this PFO5 and PFO4, and other molecules in the serum of the people. So I think the rubber meets the road when you say chemical X is being discharged into the water, and you then find it in the drinking water of people, and it is bioaccumulating in the people's blood, that risk assessors really take notice. And I think this should be sort of the route when we find things. Do you find it in the biota, whether that be people or fish in the area that are exposed? Because then it, I believe, takes you to a higher level. So other things we can do with this data. If you do high-res work, you're left with many, many, many terabytes of data that, if stored properly, can be gone back to again and again. And in this example, we can do trend analysis. You don't really need to even know what the molecule is. You can just look at what chemicals go up and down as a treatment happens or as time passes. It doesn't require one to know what it is. Cluster analysis, putting all those features found into clusters. It's easier to maybe break down this block and say, well, what are these 28 compounds? Why are they associated with each other? They could come from an industrial process that's different from this industrial process. It helps us take that big pile and separate, like we do as human beings, into separate piles to make it easier for us to look at. Fingerprinting is absolutely a technique that can be used. In this example, these were AFFF formulations. I guess there's 6 of them there. And we sort of just looked at, well, what feature shows up in formulation 1, 2, 3, 4, 5, and 6, and how do they differ? I can point this one out clearly. One of these AFFFs, the one in blue, had a feature that none of the others have. Well, that's a unique quality that we can then sleuth and say, this AFFF is the only one that has this. So if found in the environment, it has to come from that AFFF. And the last example on sort of the way we can do data mining is previously undiscovered compounds, going back in the future for things we didn't look for before. And in this example, I will tell you about HFPO trimer acid. Most people know about HFPO dimer acid or Gen X. We've done a lot of work here in North Carolina, and a lot of people do that as well. I believe it's on the drinking water method for EPA. So a lot of people are looking. Well, in 2017, Pan et al. Published on this molecule, trimer acid, being in the rivers in China near fluoropolymer manufacturers. And if you know anything about this compound, actually, if you make HFPO dimer acid, this is made as an impurity, but it's quite bioaccumulative and quite toxic. It's recalcitrant. And so companies within the United States that I've spoken with, Chemours, do not want to release this. They know this, and so they capture it and they do something to control it. At all nations, this doesn't happen. It's actually a really good polymer processing aid. And I was asked from the state of North Carolina, do we have this molecule in the water in North Carolina? I kept saying, no, I did not. No, I did not. I never saw it. Well, sorry, wrong direction. In hindsight, I said, well, let me take one more look. So I went to the monitoring wells on the Chemours facility looking for that very molecule. And the first thing I looked for was the M-H peak, and it was not present. I looked for a classical loss, which is a CO2 loss. Gen X loses this. I can see a little bit of signal, but nothing to write home about. I then looked to see, well, if it fragmented at this oxygen linker, still really nothing to write home about. So I was still feeling good about telling the state it was not present. However, I finally pulled out, well, what about if I use this diagnostic ion? This is a C3F7O. And as it turns out, I get a very strong peak at that time, but this is not a specific ion. As it turns out, this is another molecule at that facility, PMPA, which has a common fragment if it loses a CO2. So I couldn't distinguish whether or not it was truly HFPO trimer acid until I looked for the gas phase proton dimer and the gas phase sodium dimer, and they co-elute at the exact retention time, and they differ by that exact molecular weight, that 21.9819. So as it turns out, I was not looking all along for the correct thing. And I've been doing this for a number of years at that facility, but I could go back to that data, pull out that data, and spend some time looking at it because I have knowledge now that I didn't have before to then actually sleuth and answer the question for the state. Actually, that compound is present and we now know about it and could do some analysis for targeted work, and we could say something, about concentration. So the other thing I want to start to talk a little bit about is these novel compounds we've discovered at the New Jersey facility near Solvay. We were first approached by the state of New Jersey to look for PFNA in the surrounding drinking water because they had a problem in UCMR3 with PFNA in their drinking water. And as they took samples around the Solvay facility, I think it's in West Deptford, New Jersey, we were not really finding PFNA that could sort of be pointed at coming from the Solvay facility. But what myself and my group, James McCord and myself, and John Washington at EPA in Athens found in water and in soil were these chlorinated species that when we fragmented them gave this unique fragment where I showed it on the slide before. It's a ClCF6O, but we also saw the gas phase dimer. So again, mathematically, this is simple. Take that molecular weight, double it, add a proton, and I see a gas phase dimer. I know we also saw the sodium dimer. And so as we went in, we published this in Science just last year, we could identify all these fragments. We could come back and say, we know it's this compound. As it turns out, it's actually a suite of industrial compounds. It's not just one of them, much like all other polyfluorinated compounds. When you find one, you find many. And we found many, and they were in water and soil. And some follow-up work that I mentioned earlier with Anna Roebuck, looking at fish and sediment and passive samplers, et cetera, looking still for these molecules. And as it turns out, they're quite complex because this is a Marcouche structure. And so this is the Cas number. It's the ammonium salt form for that Cas number. But there's this ethyl linkage and there's this propyl linkage. And you can have 0 to 4 of these, and you can have 0 to 4 of these. And so as we begin to sort of put these compounds together and look in the environment, we have this distribution of, I guess you could call it a homologous series. Really, it's an oligomer made up of the central unit being one or the other, and in repetition, retention time wise, sort of tapering off, with the biggest one being one. Um, in hindsight, I went and looked at some samples that had been taken back in 2014. I have a collaborator in Italy. She presented this at Dublin back in last year. Her name is Sarah Valasecchi. And those samples were taken near a Solvay facility in Italy on the Bormida River. This is a known location to make polyfluorinated compounds by Solvay Specialty Polymers. And as it turns out, those same molecules were present in that water as well. In addition, PFOA was present, which was sort of why they were first at that location. And I only was able to do this because I ran these on a high-res piece of equipment, bank that data, and could go back and look and tell my colleague, yes, it's not only in New Jersey near the Solvay facility, it's also in Italy near the Solvay facility. What's the common denominator? It is Solvay. And so that gave us much more information to be able to go to the regulators in New Jersey and tell them, we have a pretty good feeling we know where this comes from, and we have a pretty good feeling we know who it comes from. And that basically gave some credibility to that. But being able to go to that old data was no question very valuable. Going to that old data as well turned up an additional compound. This might not be on everyone's radar yet, but this is a new polymer processing aid that Solvay was using. They call it C6O4, which is kind of funny because if you actually count the oxygens, there's 6 oxygens on this molecule. Carboxylic acids must not matter. But it's to replace what it was that was being used prior to that. They were using Surflon, or they were using the chlorinated species I talked about. But in Europe, it's well known that they're using this molecule, and it's a polymer processing aid being used to make either PTFE or PVDF. And there's definitely a commercial standard available for this molecule. You can get it from Wellington. We've done this, we've confirmed it, but I could go back and I can look at that old data from my colleague Sarah Valasecchi and ask the question, was this molecule present at the time? 5 years ago, I had no idea about any of these. And as it turns out, it was present. Here's that molecule. It exists as an M-H. I can see its molecular weight. I did not have a QTOF at the time, so I do not have fragmentation, but I have contemporary samples I'm working with now where I can fragment the standard and I can fragment the native compound and the unknowns. And as it turns out, I also saw the proton dimer and the sodium dimer of that very same molecule, lending credence to the fact that it was always there. I just didn't know about it. And as it turns out, you can see a trimer and you can see a tetramer because there was a whole lot of that compound. So going back 5 years from now, 10 years from now, and looking at the data that is properly acquired and then is properly sleuthed is a very, very valuable tool. Sorry, somebody's trying to call me. So to wrap up, I think I can convey to you, the value of doing high resolution mass spectrometry work. I was hoping to present at PitCon this year to people that are doing targeted analysis on a standard low resolution triple quad to start doing scans, because those of you and I that do targeted analysis tend to look for the suite of analytes we look for, and we do no sleuthing beyond that. And in doing so, we actually are sort of hamstringing ourselves into only seeing the things that are present in that method we run. High resolution mass spectrometry has the benefit of, you don't have a preconceived notion of what to look for. Low resolution, most people only look for that which is on their list. And so put those two together. There's a lot of triple quads out there. Not everybody has a high resolution piece of equipment. And so myself included, um, do an MRM acquisition of what is in your sample, but throw a scan in there because you can still do novel compound discovery with a low res piece of equipment. Using those two things in concert is probably the best bet. But if you don't have high res, obviously you can't do it. Find somebody to work with, super powerful. And it's absolutely a tool that, I can't live without. And I guess the last one is, we're always going to have more knowledge in the future than we have now on many of the things we work on. I gave you multiple examples of going back and looking. And there's no question that if we use that tool, acquire the data, store it properly, hope your external hard drive doesn't fail or you back it up somewhere well. There's no reason we can't go back from years from now and look at data that was acquired and discover things that we didn't know at the time were important. And I think that lends a lot of value to this type of work. Instead of biobanking or sample banking, we can data bank and sort of do the same type of investigation. So with that, I think I'll just close, open it to questions. Here's my contact information. If you need to email me, I'm glad to respond. And here's my disclaimer. Anything I said is my opinion and nobody can sue me. Or maybe you can, but you won't get far. So Isaac, I don't know if you want to be the one who is the facilitator of the questions, if we
Yeah,
have any.
Mark, I can take that duty if you would like. That makes it easier for you. Excellent talk. Thank you. I see that the chat section is slowly starting to blow up with some questions. The first question we have is from, let's see here, Mr. Joseph Braun. Could the breakdown of Gen X explain why it is infrequently detected in human serum samples with the general population?
That's a good question. I think it's probably not likely. And here's why I would say that. I have done some work on trying to biologically degrade Gen X, and it really doesn't degrade. So I think the reason it's not found often in human serum is because it's rapidly cleared. Even in the people living down in Wilmington that we know were being exposed to Gen X up until the time Comores, trimmed out their effluent going into the river, and we saw a decrease in the drinking water. There was a little bit of time that sort of went by. I think it was 4 to 5 months. We still did not detect it in the blood of the people living there. So I suspect it's likely that it's fairly rapidly cleared from the human body. Um, that's what we see in rodent studies. It's rapidly cleared relative, like PFOA is a good example, or PFOS. The half-lives are extremely long, and we don't see that for Gen X in the rodent. So I think it goes into probably the same in humans.
Awesome. Thank you, Mark. Joseph, I hope that answered your question. The next one is from Rachel. It's a data management question. Do you convert your data into a non-proprietary format so you don't have to worry about retaining old software 10 plus years down the road?
That's a great question. My answer is no, I don't do that because I just only use the proprietary software. My current colleagues and postdocs would give you a different answer, and I think they would tell you, yes, they do that. They transform it so it's easily convertible and importable into other pieces of software. So it depends on who you ask. I don't do it.
Okay, moving on to the next question we have from a Miss Linda Birnbaum. So doing the untargeted analyses, what percentage of the PFAS still remain unknown?
Now, Linda, that's a hard question for me to answer, but thank you for the question. Um, it's really hard to say because for example, total organic fluorine is a really good tool to try to get a handle on, well, what is the bulk of all the fluorine that is out there in an environmental sample or human serum sample. And if you sort of have that as the baseline, we can then compare it to the molecules that we can acquire and measure well, and we can compare the two. And up until now, I don't think there's a good handle on what is the total of the organofluorine. There are techniques that are moving in that right direction. Others do this top assay, total oxidizer precursor. they're all sort of getting into the same direction. But if you sort of look out in the literature, there's a lot of fluorinated compounds that are not polyfluorinated compounds that exist. Pharmaceuticals are a good example that you and I might have in our bodies that are fluorinated compounds, but are not per and polyfluorinated compounds. So the jury is still out, but I appreciate the question.
Let's see. From our very own lab postdoc, Yitka, um, compounds slash spectra discoveries in the samples depend on the extraction method we use. How much time do you think we could have? How much time or affordability would you recommend to spend on this step?
That is a great question, Yitka, and I kind of just glossed over that. I completely agree. Depending on how you do your extraction of your sample, you bias your data as to what you're going to see. If you do wax, weak anion exchange versus simply a protein crash, you see different things. My opinion would be I try to do as little as possible with sample preparation so I don't bias my data any more than need be. Now, that's a slippery slope because if you just inject a direct urine or blood sample on a mass spec, it's not going to last long. But I also want to say it depends on what you're going to do with that data. If I'm only doing polyfluorinated compounds, most of those have a negative charge on them. They're anionic, whether a carboxylic or a sulfonic acid. I can do a lot of things to get rid of the matrix interferent. If I'm doing non-targeted screening and any chemical is possible, I really don't want to bias my data by doing something like weak anion exchange. So at that point, I might do like a solvent extraction or a protein crash. So how much time should you spend? My opinion is as little as possible so you can get to the interesting work. But you have to balance that with, are you going to kill your mass spec or are you going to make your data unusable for other chemicals down the road? So hopefully that dances around the question a little bit. That's where I'm sort of usually going.
Okay, next one is from Dr. Reiner Lohmann himself. Do you know anything about how Solvay made these chlorinated ether acids? Why do the propyl or ethyl groups vary in number?
I don't know, Reiner, how they made these. It's probably in the patent literature. Like most of the polyfluorinated compounds, you have a couple of starting compounds, you put them together, you catalyze it. You're trying to get a sweet spot of molecular weight. And for these compounds, to do the job they're designed to do, that doesn't necessarily always have to be a specific chemical. It can be a suite of these chemicals that sort of hit the sweet spot. And it sounds to me like from the industrial chemist I've talked to, it's a fairly common practice by industrial synthesis. You put the starting components together and you get what you get. And does it do the job that you need it to do? And if not, you can either isolate, purify, or rerun the reaction to get it more tailored. But that's about all I know about the process.
Okay, we have one question from Maya. Follow up with what you just said with Yika's question. Is it possible to do non-target with samples that were not initially prepped for non-target?
That's a good question. The answer is yes, because I do it all the time. But for instance, let's say I have a water sample that comes in and I process that sample to look for targeted perfluorinated chemicals. I use weak anion exchange for most of that work. So my bias would be I'm doing non-targeted screening, but I'm only going to get species that went through that process and were accumulated on a wax cartridge and were eluted off. In that process, you can actually accumulate species that are neutral. So most of us discard the neutral fraction that sort of goes away when we wash the wax cartridge. If you capture that, PFOSA is a great example, comes out in that fraction, you can combine the two and look. So yes, you can do non-targeted screening. Um, if you know in advance you're going to do non-targeted screening, that's not the approach I would take, but I do it fairly regularly because most of the chemicals I work on still have that negative charge on the end, and it's still going to be captured, but it might not be a molecule that I already know about. So I don't know if I directly answered your question or not. The answer is yes, but you could change it if you kind of knew in advance you were going to do NTA.
Cool, Maya, I hope that helps. Okay, a question from Dr. Slit. Do you think that the total fluorine burden for humans is going up or down based on what you are seeing with other species?
Excuse me. That's a good question. Back when I finished my PhD, I read a paper by Key and Criddle that talked about fluoroorganics in the environment. And it wasn't just perfluorinated chemicals that I've been working on now, but there were a host of pharma compounds and lots of other species being made that were fluorinated. So sort of the short answer is probably I don't know. I think the long answer will be we'll know in the future. I'm on a project with Tom Webster at Boston University to try to answer that question. I think samples are arriving today in human serum. We're going to look for organofluorospecies and how much of that burden is explained by things we know and things we don't know. Um, so maybe stay tuned for more, but I would imagine it's moving in the direction of more than less. And I guess compared to other species was part of that, right? It was a body burden in humans compared to other species.
Yes.
Um, I haven't done other species work in quite some time. Amy Dolinsky was my postdoc the last time I did that work on fish, going back to, the maybe 2010 or so. And I've done a little bit of work with Greg Cope over at NC State and one of his students. So I don't know how much I have to compare to. I think getting back into fish would be a good thing for me to do with some of my colleagues and sort of look and see how things have changed with time, but I don't have an answer for you yet.
Okay, excellent, Mark. That I guess that wraps up the questions for now.